Okay, in this video we're going to take a look at graphing a rational function. I've given us f of x equals x squared over x cubed minus 4x squared. Okay, and I want to do the usual stuff. I want to get intercepts, asymptotes, maxes and mins, points of inflection. I've added to the directions here. I also want to check for symmetry and for holes in the graph. And I'm going to do that first step first, because I'm noticing that I can factor out an x on the bottom here, and then it's just times x squared minus 4. So then I could cancel an x. Now I need to be careful when I do that, because this function is not the same as this function. This function is the same as this. I need to record that x can't be 0. I'm not allowed to change the domain, so I get this formula as long as x isn't 0. But if x is 0, it's undefined because that would have made the original denominator 0. Okay. But that really strongly suggests that there's going to be a hole in the graph there. Because notice, originally 0 made both the top and the bottom 0. But now it no longer makes the bottom 0. So it's not going to be the location of an asymptote. Rather, it's going to be a hole in the graph. And I find the value of the hole by plugging 0 into this function. Now, why can I do that? Well, because I know that these functions are the same except at 0. So the limit of this function is the same as the limit of this function. But I would evaluate the limit of this function at 0 by just plugging in. So the origin is going to be a hole in the graph. Okay. Now, that means that there's no y-intercept because I'm not allowed to plug in 0. If I check for any x-intercept, or septs, I would set the function equal to 0. And I can now work with this version of the formula rather than this one, as long as I just keep making that mental note that x isn't 0. Okay. So, x over x squared minus 4 would equal 0 with the restriction that x isn't 0. Well, the only way to make that true would be to make x 0, which we can't do. So there is no x-intercept either. Let's check asymptotes. Okay. There are two numbers that are going to make the denominator 0. This is x over x plus 2 times x minus 2. So I can see that both 2 and negative 2 make the denominator 0, but they don't make the numerator 0. So I'm going to have an asymptote on either side there. Now, if I go to check for horizontal asymptotes, that means I want to take the limit as x goes to infinity of x over x squared minus 4. Definitely fine to use this version of the formula here, because if x is going to infinity, it's not going to be 0. And I also need the limit as x goes to negative infinity of x over x squared minus 4. And I've got several options for how I do these limits. First of all, this is a rational function, and we're going off to infinity or negative infinity. I am fine in a problem like this, especially since they're long problems to begin with, if you use the shortcut that if we're going to infinity or negative infinity, a rational function is dominated by the fraction of its lead terms. So this would be the limit as x goes to infinity of 1 over x, which is just 0. So I know I'm going to have a horizontal asymptote on the right. Now, if you remember, when we first studied these sorts of limits, I gave you that shortcut, but we also learned how to formally justify it. I'll remind you of the formal justification for this limit. The formal justification would have been to multiply by 1 in the form of the reciprocal of the biggest power on bottom over itself. So then this becomes the limit as x goes to negative infinity of x over x squared becomes just 1 over x. Well, let's write it out. X over x squared over x squared minus 4 over x squared. So that's the limit as x goes to negative infinity of 1 over x over 1 minus 4 over x squared. The two pieces with an x in the denominator go to 0, and so we get 0. So we'll have a horizontal asymptote on the left side. as well. And there is a third option. Where did I put the, here it is. Need to erase the board. There is a third option for evaluating these limits at this point. I could observe that the top's going to infinity and the bottom's going to infinity, and I could L'Hopital it. So I could say this is the limit as x goes to infinity of 1 over 2x, and that's still 0. Okay. So I'm going to have a horizontal asymptote on both sides of my graph. Okay. Now, if I look at this, I've got asymptotes at mirror image places, I've got horizontal asymptotes at the same height. It does seem reasonable to check for symmetry here. Sometimes, after you've figured out the asymptotes and the intercepts, you can tell there's no symmetry. Because if I had a vertical asymptote here, but not here, I wouldn't have symmetry. Okay. But here, let's check. Okay. Now, I'm going to go ahead and use this version of the formula. So I'm going to say if x is not 0, then f of the opposite of x, I'm just going to plug in the opposite of x. So I get the opposite of x over the opposite of x squared minus 4. So that's negative x over x squared minus 4. I can bump that negative to the front. That's the opposite of x over x squared minus 4. That is negative f of x. So this function is odd. It has rotational symmetry or symmetry about the origin. Opposite inputs are going to give me opposite outputs. Okay. So we will have symmetry about the origin. Okay, excellent. So I think that's everything we can get from f. So let's now take a look at our first derivative. Now I'm going to use this formula and just make a note that for the first derivative, that's also going to be undefined if x is equal to 0. But then I can say f prime of x, and I'm just going to use quotient rule. So I'll get low, x squared minus 4. D high, the derivative of the top is 1. Minus high is x. D low is 2x. All over, square the bottom, and away we go. So that's x squared minus 4 minus 2x squared all over x squared minus 4 squared. That's going to be negative x squared minus 4 over x squared minus 4 squared. That is always defined on the domain. Now, it's not defined at 0. It's not defined at plus or minus 2. But those aren't going to be critical numbers because they're not in the domain of the function. So they're not possible locations of maxes and mins. They are important. When I draw my number line, I'm going to include those points because we've certainly seen functions that increase on one side of an asymptote and decrease on the other side. So the derivative could change sign here, but it won't be a location of a max or a min. So I just want to see where this thing is 0. So f prime of x would equal 0 if the top is 0 and the bottom isn't. Of course, with the restriction on all of this that x isn't 0. But that's not going to be, oops, this would have to equal 0. So negative x squared would have to equal 4? I don't think so. This actually has no critical numbers. It's not going to have a max or a min. It has neither of those things. Let's see, I want to keep written down what my first derivative was. So f prime of x is negative x squared minus 4 over x squared minus 4 squared. We'll keep that in with x not equal to 0. Okay, but let's now draw a number line for f prime. I still do need to draw one. So I'm going to keep that up. That's my f of x. I'm going to draw a number line here for f prime. Now I don't have any critical numbers, but I want to mark off negative 2, 0, and 2. I want to mark off the 3 places where my function is undefined because it's possible that my derivative changes sign there. Now I am going to make a note. This is a vertical asymptote, that's a vertical asymptote, and that's a hole. So even if the derivative does change sign and the function changes direction, I won't have a max or a min. But I do still need to check this. So let's just plug in -3. Let's see, that's going to be a negative on top and a positive on bottom. Actually, I don't really even need test numbers because I can see the top is always going to be negative and the bottom, because we're squaring it, is always going to be positive. This function is always going down. Okay. Kind of exciting. Okay. Okay. So, that's what we have there. Now, we still need to take a look at the second derivative, look at concavity and find points of inflection. I'm going to stop this video and just start that in the next one. So we'll continue this problem with the second derivative immediately in the next video.